Okay, ready.
Okay, so the previous lecture talked about nuclear weapons and how they work and so on. We also touched on nuclear testing. Now let's talk about nuclear weapon effects. What are the effects of all these massive weapons that were tested and that were actually, you know, the Japanese cities of Hiroshima and Nagasaki were bombed? What were the effects? So first, the bombings were, as you know, horrible in 1945. It produced many fission products that are radioactive, incredible devastation caused by the pressure wave, the blast wave, the heat that caused firestorms. We're going to talk about that, and the radioactivity that's left over. Many fission products that are left over, and so these are cesium-137 and strontium-90 that I mentioned earlier that produce the bullets, right? That's the stuff that we're afraid of, the gamma rays and so on, that can hurt you because these bullets are coming off of the material and they hit you, they destroy your cells, and so can make you very sick, cause cancer and so on. All the damage stems from the energy release that's converted to particle, light, or object. So this explosion happens like this. You have the blast wave that comes out, and that's like a huge wind that comes out and that carries different materials, and these themselves become like little missiles. There's the energy that's released in terms of electromagnetic radiation. There's the bullets that are coming off. All this kind of stuff that I'm talking about. Again, right, the bullets are an analogy. I'm not talking about real bullets. I'm talking about gamma rays and so on that act like bullets because they can damage your cells inside your body. So when you talk about the partition or how the energy is separated from, let's say, whatever the TNT yield is of a bomb, 50% is in terms of blast waves. And so this is the energy from the shock wave that comes off. And this is the energy in compression. We're going to talk about that in some detail. 35% is the thermal energy release. And this is the electromagnetic radiation that heats materials and so on. And then 15% is the nuclear radiation, where 5% is the prompt neutrons that are released and gamma rays, and the rest, 10%, are the fission products that are left over that decay over time. So this is how the energy is partitioned among the three different energy sources. So let's talk about the blast wave, which is 50% of energy. Here I'm showing kind of picture of, let's say, oops, I'm sorry, dropping a stone in kind of a quiet pond, right? The waves will travel out in concentric circles and disturb the water. Well, of course, when you're talking about nuclear weapon, I really don't think of it a quiet pond at all. What you have is you have a spherical wave, shock wave that travels outward like this, and not in concentric circles, but in 3 dimensions, it's spheres that travel out, and they disturb the air as it's traveling through the air. The shock waves, as they travel out, compress the air in front of it. And this compression causes a pressure to increase. And that's measured in pounds per square inches. And that's really the effect that you have from a bomb. So this shows you what's called an air burst. And so what you do in this case is you have an explosion which is not on the ground, because you can see the ground at the bottom here. It's actually exploded a little bit above the ground. And the reason why you do that is because you get a reflected wave which reinforces the pressure and makes even a higher pressure and a more higher effect of the bomb. And so you can have an even more damage. That's called the Mach stem. So the blast wave is reinforced by a reflected wave. And so you can kind of see that in this picture here, where you have at different times, you can see how this blast wave, so T1, T2, T3, T4, is later and later and later in time as this blast wave from the bomb that's detonated at a certain height above ground zero or above the surface explodes. and then you see the shockwave move outward, reflect off the ground, and then interact with that incident wave, spherical wave that's coming out. So reflected wave and the incident wave are interacting. So you have the one pressure, pressure one, and then the other one, another pressure. So adding up together, you have even more pressure, and even more pressure, more damage. In fact, it's about a factor of 2 in terms of the damage that you have. So this is kind of a video that describes the effect in more detail.
Pressure intensified around 500 meters from ground zero. We filmed that movement using a special device that can detect invisible flows of air. Here's how the blast expands from the center of the explosion. When the blast wave strikes the Earth, it is reflected upward to form a second, dome-shaped shock wave. Let's focus on the area where the 2 waves meet. One shock wave comes from above, as it expands from the core of the explosion. The other is reflected off the ground. The 2 blast waves then merge, more than doubling their individual pressure, and continue expanding in a horizontal direction. The combined wave grows in height and strength as it moves along the ground. This is the shock wave, known as the Mach stem.
We used a very small amount of explosives, but something much bigger like an atomic bomb or a huge amount of explosives or explosion would have generated the same kind of shockwave movement. The result of our experiment is in line with what happened in Nagasaki, where Mach reflection occurred at a short distance from ground zero and caused severe damage farther away.
Okay, so that's the idea, is that you exploded above the surface so that you get reflection from the ground, and this reflection interacts with the wave that was already going outward. So you increase the pressure and you increase the effect. So the blast wave itself travels outward and pushes air outward, and it compresses it. And when you're compressing it, it produces a higher pressure. And it's this pressure that you feel. So you have 2 different effects. One is kind of a wind that travels outward, and that they call dynamic overpressure, which is going to be very high speed wind, which if you're talking about nuclear weapons is so much worse than hurricane winds, extremely high speeds, the winds. I'm talking about 1,400 kilometers per hour winds. So very, very intense high speed winds. But then you also have this static overpressure, which increases the local pressure of at a particular point. So that's really what I'm saying, is when you have a higher pressure because the air itself is being compressed. So the body is kind of squeezed inward, kind of like diving too deep, and the lung can collapse. So this is kind of a crushing effect that you have. And the pressure as a function of distance from the explosion is related to the yield. And of course, this makes complete sense, because if you get closer to where a bomb explodes, of course, the effect is going to be higher than if you're further away. And the way you measure effect is in terms of the pressure that you feel as this shockwave moves outward. And when you talk about hardening so let's say a missile silo, it means the pressure that you need to hit it is higher, which means that you also need a higher yield needed to destroy the silo. So here you can kind of see the effect here. If you have a peak overpressure of something like 100 psi, which pounds per square inch, which is a large effect, but you know, of course you get that during explosions. Then that wind velocity is like 1,400 miles per hour. So that's like 2,000 kilometers per hour. So this is a very, very high wind velocity that you would get. And here you kind of see what would happen, what a particular location would experience as the wave would travel through. You get this massive wind, and then a little bit later you actually get a pressure that goes the other way, it actually suction towards ground zero, which I kind of try to show here. And further away, as this wave, this blast wave, starts losing its strength, losing its energy, as it gets further away, the peak overpressure will become less and less and less and less, and the effect will be less. Okay, so if the bomb is detonated on the ground, so it's not necessarily detonated above the ground, but it's actually detonated on the ground, then you have this massive mushroom cloud, which you're familiar with. You can also have mushroom clouds when you have a detonation above the ground, but it's more associated with ground explosions. And as you know, conventional bombs also have mushroom clouds. So just because you see a mushroom cloud doesn't mean it was necessarily a nuclear explosion. So this is what a ground burst looks like. And what you see is this shock front. It's very hard to see here, but you see a shock front that moves outward here. So on the outside, the air hasn't been compressed yet, so it's undisturbed air. But as this shock wave moves out, this sphere at which there's a high pressure, as that moves out, it's going to cause many different blast wave effects. And here you can see the shock wave. I really like this slide because you can see how the shock wave is disturbing the pressure of the air. And that's because you disturb the pressure of the air, it almost looks like you're looking through like a lens, as you can see as the shock wave moves outward. This is not a nuclear explosion, this is a conventional explosion, but it's very useful to seeing how that shock wave travels outward spherically. An analogy is kind of like this kind of glass hemisphere, where this glass hemisphere is basically a different pressure, almost like a different material that comes out and travels through the air. Now, a very important thing and a very important takeaway from this lecture is that a blast effect is not linear. And this may sound counterintuitive, but I think you'll see that it's quite intuitive. What I mean by that is if you have a 10 kiloton explosion, so this is the order of Hiroshima and Nagasaki, but then you have a 1 megaton bomb, which is 100 times more larger yield bomb than a 10 kiloton bomb, then you would kind of expect that whatever pressure effect you have, let's say that you have a concrete building collapse at 1 kilometer, then maybe because the yield itself is 100 times more, you would expect that for a 1 megaton bomb, the concrete buildings would collapse at 100 kilometers. And it would go because it's such a much larger bomb. But in fact, that's not the case at all. Concrete buildings collapse at 1 kilometer for a 10 kiloton bomb and only 5 kilometers at a 1 megaton bomb. By no means am I belittling the size of these explosions. These are massive, massive, massive explosions and the damage that they can do. But it's not a linear process that if you have 100 times larger yield, that necessarily means that the same effect from the blast wave is going to be 100 times further than it would be at 10 kilotons. And when you think about it, I said it was not intuitive, but it's actually quite intuitive. If you think of the effect of a 10 kiloton bomb as kind of being a small ball of a certain radius, okay? So the size of that ball represents the size of a 10 kiloton, the sphere of a particular effect, let's say concrete buildings collapsing, 100 psi, at a certain radius. Now, if you have a 1 megaton bomb, that's like stuffing 100 of those little balls in a balloon. And as you can see, that balloon won't expand 100 times its radius. It expands only a little bit times the radius of these small little balls, if you have 100 of these little balls. So the effect is not linear. So it kind of makes sense that the blast wave effect is not felt as far as you would have had expected. And there's a more technical explanation, but I think this is really the main point. There's an excellent website done by Alex Wellersteins, and you can just type nuke map in whichever search engine that you use, and you'll be able to find it. And what you see here, this is a 10 kiloton explosion on Monterey, and this is a 100 kiloton explosion. And what you can see is that where that arrow itself only moves out, because you moved from 100, this is 10 times larger explosion, it only moves out about a factor of 2. So that's the effect. The lethal radius, for example, only changes a factor of 2, even though the bomb is 10 times larger. But by no means am I saying that these bombs are not extremely large and extremely terrible. So let's talk about the effect of thermal radiation, which is 35% of the total energy. So when you have a bomb, you're creating an object on Earth that's actually hotter than the sun. It's 1,000 times brighter than the sun, and it'll burn everything. And now the bullets itself is the intense light that comes off at different wavelengths, different frequencies. And these little photons, as they call it, the little light particles, each of them has a little bit of energy that's associated with it. And so if you have a lot of energy, because you have a lot of these little light particles hitting, let's say, a square centimeter, depending on what the material is, the energy will be so high that you'll start burning the paper or something. So it's essentially like you're concentrating light with a magnifying lens. When you concentrate all that light, all those little photons in a very small spot so that the material starts to burn. It's essentially like that, except no magnifying lens is necessary. You just start to burn grass. If you had a 100 kiloton bomb, you can ignite grass at just 3 miles away. So it will just start to burn the grass spontaneously. And this will cause massive, massive fires. A 1 megaton bomb will give a serious sunburn from 20 kilometers away and a 3rd degree burn at 11 kilometers. So these are these horrible effects of the thermal effect of nuclear weapons. And depending on so this is really the energy density, which is the number of photons, the amount of light, the concentration of light that you have in a little centimeter squared. If it gets to be higher than a certain number, so let's say 15 cal, this is just a unit of energy per centimeter squared, and then newspaper will start to burn, or dry wood will start to burn, or deciduous leaves will start to burn, or grass will start to burn. And so that's where the argument that I just explained was that a 100 kiloton bomb can ignite grass at 3 miles. If we look at these effects as a function of distance, and this is data from horrible casualty data from, I believe, from Hiroshima. If you look at the distance from where the explosion happened and the casualty rate, if you're in this area very close to the bomb, quite obviously, a lot of the people died here because of the blast injuries, this massive wind, this massive pressure difference that killed a lot of people. But at 1.5 kilometers, 50% of the casualties are due to the blast wave itself, the effect, and 50% are due to burns at 1.5 kilometers. Further away, you get other thermal effects, and other things will dominate the fatality rate. But you can see now how this casualty rate is different. And I think these are the 2 different bombs. Sorry, I think these are 2 different bombs that happen. So further away, the effects are going to be less. Now let's see the effect of what a bomb does on, say, a house. And so you can see here the light which arrives first, because it arrives at the speed of light. Of course, the shock wave travels much slower. You can see the paint on the house starting to burn as the thermal effect becomes stronger. And now the blast wave arrives, and you can see what the damage is, what damage it is doing to the house. It's pushing up the roof up like this, and it's, you know, causing massive devastation. And then later and later and later, and you have full destructions of the house within less than 3 seconds. Along with the thermal effect, you have the effects from the fires. So as I was saying, you burn grass, but you can burn lots of different things. And you can have, you know, these massive fires that that burn, and fires that combine and form large super fires, and firestorms that that develop, that have their own kind of weather patterns effects that kind of sustain the fire, and let the fire become worse and worse and worse. And we know all about these massive fires here in California with the forest fires. So firestorms developed in Hiroshima about 20 minutes after the explosion. The deaths caused by the heat, or when they're in shelters, they suffocated, so the fires themselves took all the oxygen out of the air, and so on. This is all really horrible. So this is just a summary. The blast effect is a shock wave that moves outward and destroys everything in its effects. The effects are 2 types of overpressure, but the effect is not linear with respect to standoff distance. So distance that you're away from where the hypocenter, where the bomb exploded. The thermal radiation causes mass fires and unspeakable horror. Okay, stop recording.